Welcome to The Explainer. You know how running the latest, greatest AI model feels like it needs a supercomputer? Well, you're not wrong. Today, we're jumping into a really important paper about AI efficiency to tell the story of one specific architecture that's completely changing the game, RWKV. So, really, why are these models so incredibly expensive to run? The thing is, it's not just that they're big. The answer is baked into the very DNA of modern AI. The transformer architecture, which is the foundation for almost everything, it comes with some serious and often hidden computational costs. So, here's how we're going to break it down. Think of it like an hourglass. We're going to start broad with the big problem facing AI, then narrow our focus right down to our case study, RWKV, and then we'll zoom back out to see just how big its impact really is. All right, let's get into it. To really understand why something like RWKV is such a big deal, we have to talk about those hidden costs. We need to get to the bottom of the core bottleneck that's, frankly, slowing down the entire field of AI. Okay, this right here, this is the whole problem in a nutshell. Standard transformers have this amazing thing called self-attention, but it has a dark side, quadratic complexity. What does that mean? Well, it means if you double the length of your input text, you don't just double the work, you quadruple it. But these newer, efficient architectures, they're aiming for linear complexity. So you double the input, you only double the compute. And trust me, that isn't just a small improvement, it's a total game changer for what's even possible. So with this massive scaling problem staring everyone in the face, researchers started looking for a totally different way forward. And it's funny. They actually found inspiration by looking backward at an older, maybe even misunderstood type of model. And that search led to this big comeback for something called recurrent neural networks, or RNNs, specifically a type called linear RNNs. It turns out by just tweaking them a little, removing certain complex parts, these models could suddenly be trained in parallel, just like a transformer. But, and this is the absolute key, when you're actually running the model, it works sequentially, one step at a time. That makes it lightning fast and super memory efficient. So all this new excitement around linear RNNs, it created, the perfect storm for a new player to enter the scene. And that brings us to the star of our show today, RWKV. The paper that first introduced RWKV just laid it all out there. The goal was huge, incredibly ambitious, to get all the power and the fast parallel training of a transformer, but squeeze it all into the super light, super efficient engine of a classic RNN. So how on earth does RWKV pull this off? Well, it's kind of like a shapeshifter. It operates in two totally different modes. When it's training, it acts like a transformer, gobbling up data in parallel so it can learn super fast on modern GPUs. But then when it's time to actually generate something, it flips a switch and acts like an RNN, going one word at a time. This means it doesn't need that giant, ever-growing KV cache that just cripples transformers. And that is the secret to its speed. But the story of RWKV isn't just about one clever idea. Nope. It's about this relentless, non-stop sprint of innovation. This architecture has been evolving at a wild pace, and with every new version, it gets more powerful and way more sophisticated. And just look at this timeline. It shows you how fast this has all happened. Back in 2022, version 4 lays the foundation with a smart memory system. Just 1 year later, version 6 comes along and gives the model a much bigger, more flexible memory. By 2024, version 7, they nicknamed it Goose, gets even smarter, learning to adapt itself as it goes. Each step is a huge leap, and it all leads up to its most interesting move yet. And this is where the story gets really interesting. With the latest version, RWKVX, the project went hybrid. And it wasn't them giving up on the original idea, not at all. It was just smart. It was them realizing that to get the absolute best performance, you need to combine the raw speed of the RNN with the pinpoint accuracy of the transformer's attention. Conceptually, you can kind of think of it like this. On one side, you've got the pure, blazing speed of that linear, recurrent design. It's fast, it's light on memory, and it's fantastic for really long sequences. And on the other side, you've got the raw power of attention, which can remember one tiny, specific detail from thousands of words ago. Models like RWKVX weave these two things together, giving you the best of both. And this amazing combo of speed and power, it didn't just stay in the world of text for long. The RWKV architecture has proven to be an incredibly versatile powerhouse, and it's been successfully unleashed on a whole bunch of other fields.
So in computer vision, RWKV's efficiency is a massive, massive deal. It's now being used to power models that can segment any object out of a picture, process ultra-high-definition video without, melting your graphics card, and even help analyze really complex medical scans, where seeing the whole picture is, well, it's literally a matter of life and death. Then you've got audio. Its one-step-at-a-time nature is just perfect for real-time stuff. Think about streaming speech recognition on your phone. RWK models are giving you results with practically zero delay, keeping up with much bigger models while using just a fraction of the battery. Which brings us to multimodality, which is where AI has to understand the connection between different things, like an image and the text that describes it. And yep, you guessed it, RWKV is being used here too, to build super efficient models that can look at a picture and tell you what's in it, all without the crazy overhead of a typical transformer. So after going on this whole journey, from the big problems with transformers to the incredible evolution of RWK, what's the final takeaway? What does all this mean for where AI is headed? Well, the title of the very paper we've been looking at says it all. Speed always wins. Because efficiency, it's not just some technical nice-to-have feature, it's the engine of innovation. It's what makes powerful AI available to everyone, what unlocks new features on the devices we already own, and what lets the whole field just move forward faster. The story of RWKV is just such a great example. It proves that by being willing to rethink our most basic assumptions, we can smash through old limits. And it leaves us with a really exciting question. If speed is the key that unlocks the next generation of AI, what incredible new doors are we about to open?